Good morning, everybody. Okay, let's get started. So in the previous class, we started the discussion of root locus. What is the root locus? Anybody remembers?
It's the lines of poles where they could be.
Excellent. It's a plot that shows a plot of the roots of the system characteristic equation as some parameters and usually we choose the gain, but doesn't have to, is varied. Okay. So why is this important? Why is the root locus important? Why is it important to plot the roots of the characteristic equation, which is the same as saying the poles of the closed loop system? Any ideas?
So then you can get the main shape of the system without having to plot every single point?
Excellent. Yes, that is why this graph, being able to generate the graph is important. But why is it I want to know where the poles of these systems are?
So you can determine if it's stable?
I can determine if it's stable. What else? I can determine the performance of the system. Remember, everybody? So here, help us determine the response of the system. If you recall, when we look at the second order system, if we have a second order system, we said if we have poles in this region, what are these poles? If these are two poles of a second order system, what is the response of the system going to look like? Underdamped. It's going to be underdamped. And if I know the pole location, then I know this is zeta omega n. I know this is omega n square root of 1 minus zeta squared. I know this is theta, and cosine of theta is equal to zeta. So I know everything about how the performance is going to look like without having to calculate the response of this system. Make sense? Remember also, we said if I have two poles here versus two poles that are at this location, what is the difference between the response of the system that has these two poles versus the system that has these two poles? Which one is going to be faster? The one that is here. The farther we are from the j omega axis, the faster the response is, isn't it? So the system that has these poles here is going to have a very small settling time versus the system that has the poles that are closer to the j omega axis is going to have a much higher settling time. Make sense? So therefore, if I were to plot the root locus, and the root locus told me, oh, it looks something like this. As you vary k, the root locus, the roots are going to be along this line. Then I know for this value of k, this is the settling time I'm going to expect is going to be very large. If I change the value of k, I could be operating here, and I could have a much smaller settling time. Make sense, everybody? Okay. Now also, we said if I were to take the system, and this is the typical system that we're going to be studying, we're going to have a controller that is just a gain, and then we have a plant and we have a feedback. If I were to calculate the closed loop system, it's going to look k multiplied by g over 1 plus k multiplied by g multiplied by h. This is the closed loop transfer function. And therefore, we said the characteristics equation of the system is 1 plus k multiplied by g multiplied by h equal to 0. If I solve this equation, it's going to give me where the poles of the closed loop system are. Make sense? Okay. So therefore, a pole, if I take any point given S1 in the S-plane, for S1 is going to belong to the root locus if and only if 1 plus k multiplied by g of S1 multiplied by h of S1 is equal to a 0. Agree? S1, if I take any point in the S space, S1 is going to be on the root locus if it satisfies this equation, 1 plus k multiplied by g multiplied by h is equal to 0, which means it's a pole of T of S. Together? Okay. I'm going to slide these down. Now this is very important, and probably we should have mentioned it in the previous class, so that's why I'm coming back to this. So therefore, I can write this as k multiplied by g of S1 multiplied by h of S1 equal to -1. So again, S1 is on the root locus if it satisfies this equation. What does this equation says? It says the magnitude of k multiplied by g multiplied by h has to equal to a -1. But I can write this -1 as an angle that is 180 degrees. So therefore, I can create two conditions for S1 to be on the root locus. What are these two conditions?
The phase and magnitude.
The magnitude has to equal to a 1, and the phase has to equal to 180 degrees. So therefore, for S1 to be on the root locus, the magnitude of g of S1 multiplied by h of S1, what does it have to equal to? Close.
K.
What does it have to?
1 over K.
1 over k.
Yeah.
1 over k is okay. 1 over k. Make sense? And second, what is the second condition? The phase of g of S1 multiplied by h of S1, what does it have to equal to? 180 degrees. Make sense? Everybody? What do we call the first one? We call it the magnitude criteria. And we call this the angle criteria. Now notice here, the angle criteria, there is no flexibility in it. The angle of g of S1, h of S1 is going to be either equal to 180 or not. With the magnitude, there's flexibility. I can always control k to have that magnitude equal to 1. Does that make sense? So here, there's a parameter that I can change, which is k, to make this true. Okay. So then we said, as an example of this, if I have g of s that is equal to 1 over s multiplied by s plus 2, and I have h of s equal to 1, I want to see, does S1 equal -1 plus J1 belong to the root locus or not? What do I have to do to determine whether a point belongs to the root locus? I'm going to use the two criteria that we had before. I'm going to calculate G of S1, or G of S1 multiplied by H of S1. which is going to equal to 1 over negative 1 plus j1 multiplied by negative 1 plus j1 plus 2. What is this going to equal to? Negative 1 over 2. So therefore, if I go back to my criteria, I want g of s1 multiplied by h of s1, the magnitude to be 1 over k. And I want the phase or the angle to equal to 180 degrees. Does this meet the angle and the phase criteria? Yes, the angle of g of s1 multiplied by h of s1 is equal to 180 degrees. This is equal to 1/2, and the angle that is 180 degrees. And what is the value of k that will make this on the root locus? 2. Yes. So for k equal to 2, S1 belongs to the root locus. Does that make sense, everybody? Now let's take another point. Let's see, does S2 equal to negative 4 belong to the root locus? We're going to do the same thing. We're going to calculate g of S2 multiplied by h of S2, which is going to equal to 1 over negative 4 multiplied by negative 4 plus 2, which is going to equal to 1 over 8. What is the value of k that will make g of S2 multiplied by h of S2 equal to a 1? 8. So we can meet the magnitude criteria, but does this meet the angle criteria? No, it does not. The angle of g of S2 multiplied by h of S2 is not equal to 180 degrees. And therefore, there is no k that will make S2 belong to the root locus.
So if it's positive, that 1 over 8, that side's positive.
Yes, if it is not negative, then it's not on the root locus.
Okay, and there's no way to,
There is no way.
okay.
I mean, there is a way.
Oh.
But according to our assumption, there is no way. What is the way for this to be on the root locus?
H is negative 1.
No. If k is negative.
Okay.
But we're assuming our k is positive. So there is no way this will be on the root locus for a positive k. Remember, our assumption when we plot the root locus is k is going to be positive. Okay. So let's generalize what we just done. So let's look at the geometric interpretation of the angle criteria. So let's say that we have g of s multiplied by h of s, that is given by the following. G of s multiplied by h of s, that is equal to s minus z1, s minus z2, all the way to s minus zm. Divided by s minus p1, s minus p2, all the way to s minus pn. So we took the open loop gain, g of s multiplied by h of s, and we wrote it in this form. We factored out the roots of the polynomial. Make sense? Okay. Now, if I were to evaluate the phase of g of s multiplied by h of s, what is that phase equal to? What is the phase or the angle of g of s multiplied by h of s equal to? how do we calculate the angle of g of s multiplied by of h of s? We take the angle of this term plus the angle of this term plus the angle of this term, and then we subtract from it the angle of this term, angle of this term, angle of this term. Make sense, everybody? So if I want to calculate the angle of g of s multiplied by multiplied by h of s is going to equal the angle of s minus z1 plus the angle of s minus z2 all the way the angle of s minus zm, and we're going to subtract from this the angle that comes from s minus p1, s minus pn. Is that clear, everybody? And similarly, if I want to calculate the magnitude of g of s multiplied by of h of s, what is it going to equal to? The magnitude of this term multiplied by the magnitude of this term divided by the magnitude of this multiplied together. I mean, nothing new, straightforward. If I were to tell you, calculate g of s, g of g multiplied by h when s is equal to 5. You're going to plug in 5 here. 5 minus z1 multiplied by 5 minus z2. If you do not have a calculator, you're going to come here and write this in polar form. Amplitude and a phase, amplitude, phase, amplitude, phase. You're going to add all the phases together, subtract it from all the phases in the denominator, and that will be the final phase. And the same thing, the magnitude, you multiply all these magnitudes, divide them by all the magnitudes from the denominator. Okay. Now why we're doing this? Because I want to determine whether S belongs to the root locus. When does S belong to the root locus? If this angle is equal to what? 180 degrees. So therefore, S belongs to the root locus if the summation S belongs to the root locus if g of s multiplied by h of s is equal to 180 degrees or any odd multiple of 180 degrees. So you can just take r plus 1 and r equals 0 plus minus 1 plus minus 2, etc. And therefore, what does that mean? Using these two formulas that we have here, I can write this as S will belong to the root locus if the summation of the all angles from zeros minus the summation of all angles from poles is equal to 180 degrees or any odd multiple of 180 degrees. Together, this represents the summation of all the angles from the zeros. This represents the summation of all the angles from the poles. Is that clear, everybody? So therefore, how do we check for any point whether it belongs to the root locus or not? I'm going to take the summation of the angles from the zeros minus the summation of the angles from the poles. If it is 180 degrees, then it belongs. If it does not, it will not belong. So let's see how this will look like. So let's say I have a system where I have a zero here, and I have a pole here, and I have a pole here. P1, P2, and I have Z1. What are these poles and zeros? Where they're coming from? From G of S multiplied by H of S. Together? I mean, we're going with this derivation. G of S multiplied by H of S. It has 1, 0 that we plotted, and 2 poles, P1 and P2. Okay. Now what I want to do, I want to determine whether a point that I'm going to pick somewhere here belongs to the root locus. So I'm going to take a point here, S1. I want to see if S1 is part of the root locus or not. How do I determine if it is part of the root locus or not? I'm going to take the angles from the poles, the angles from the zeros. I'm going to take the angles from the zeros minus the summation of the angles from the poles. If it is 180 degrees, then it belongs. Make sense? This is what we've done here. This is what we're saying here. The angle to S1, to Z1, plus the angle to Z2, minus the angles to the poles. Make sense? Now I can use this mathematically, or I can do it graphically. The same thing. So therefore, I can come here and plot a line to get the angles. And let's say that we have an angle here that is phi 1. This angle here is phi 2. And this angle is psi 1. What is the condition for S1 to belong to the root locus?
The leftmost psi 1
Psi 1
minus phi 1 and phi 2 add together.
added together must be a 180 degrees. Excellent. Does that make sense? So given the open loop, poles and zeros, I can determine whether a point on the root locus by taking the angles from the zeros, add them together, minus the summation of the angles to the poles. If it is 180 degrees, then this point is on the root locus. Okay. Let's do a quick example. So we are given G of S multiplied by H of S equal to S minus 3 divided by S plus 5. I want to evaluate G of S multiplied by H of S when S is equal to 1 plus J1. How do we evaluate G of S multiplied by H of S when S is equal to this value? I just plug in that value, isn't it? So G of S multiplied by H of S when S is equal to 1 plus J1 is going to equal to 1 plus J1 minus 3 divided by 1 plus J1 plus 5. And this is going to equal to a negative 2 plus J1 divided by 6 plus J1, which is going to equal to 2.2, an angle that is 153, divided by 6, an angle that is 9.4, which is going to equal to 2.2 divided by 6, an angle that is 153 minus 9.4. Agree? That's how you would calculate it. Okay, now let's see if I want to do this graphically. So if I want to do this graphically, I'm going to come here. I'm going to plot the open loop poles and zeros. I have a 0 at 3. And I have a 0 at negative 5. A pole at negative 5 and a 0 at 3. This is 3, this is negative 5. And the point I'm trying to evaluate at is S equal to 1 plus J1. So my point here, this is S1. So what I need to do, I need to calculate this angle here. And then I need to calculate this angle here. See the straight line? Okay, what is this angle equal to? Excellent, 153. What is this angle equal to? 9.4. So therefore, if I do the angle criteria, what is the angle of G of S1 multiplied by H of S1 equal to? I'm going to take the angle to the 0, 153, minus the angle to the pole, which is going to be 153 minus 9.4. This does not equal to 180 degrees. Therefore, S1 does not belong to the root locus. Is that clear, everybody? Go ahead.
So I guess we can assume if there's only one pole, 1, 0, that it won't be part of the real locus.
In this case, or
Just
in
in any case, because their angles wouldn't add up to be 180.
no, there will be an angle here that there will be a point where it will be 180 degrees.
Oh, okay.
Yeah, there will be points where it will be 180 degrees. Why would you think it will not?
Because if it's just...
No, I mean here, if I take a point here, this angle is 180 degrees, this angle is a 0.
Oh, okay. Okay.
Make sense?
Yeah, yes, sir.
I mean, a very good question. Here is a point. This point is on the root locus. Because the angle to this point is going to be 180 minus a 0 is going to be 180 degrees. Together? Okay. Now in this case, you might be right that there might be no point of the axis that will make that criteria. That might be the case, yes. Okay. Is this clear, everybody? So again, what we're going to be doing is we're going to be using this angle criteria to determine whether a point belongs to the root locus or not. Now what we said is that we're going to be able to generate the root locus without having to use a computer. And we want to have, in order to be able to do that, we said we're going to create a set of rules that we're going to apply. We're going to go through these rules. We're going to understand these rules. And hopefully when we finish all the rules, like the full picture will come together. So each rule, I mean, we're going to explain it, we're going to demonstrate it, and then when we have all the rules together, we should be able to take any transfer function, any system, and be able to plot the root locus for. Granted, we don't do a calculation error. Okay, so what are the rules? These are all the rules that we're going to be going through that will help us plot the root locus. Good? I mean, too many rules, but it's better to have too many rules than not enough rules. Okay. So let's see. I mean, some of these rules we talked about in the previous class. So we're going to just go over them quickly. So when we have G of S, H of S, the number of branches of that are going to be on the root locus is going to equal to the number of poles of the open loop system. Make sense? So if I have a fifth order G of S multiplied by H of S, in the denominator is the fifth order, S to the 5 plus something, it has 5 poles, then it means I'm going to have 5 branches in the root locus. Make sense? Okay. Then also we said the branches of the root locus will start at the pole and will end up at a 0. Remember this rule from last class? The branches of the root locus will start at the poles, and will end up at a 0. Remember, this is the last thing we've done. When k is very small, I'm going to be operating at the pole. As I increase k, I'm going to go to a 0. Make sense? I mean, we demonstrated this, so you can go back and look at it to convince yourself this is the case. Now, what happens if I have 5 poles and 5 zeros? Easy. Each branch, we have 5 branches. Each branch is going to start at a pole and end at a 0. Together? But what happens if we have 5 poles and only 2 zeros?
Can you repeat it?
No. We're going to have 3 branches or 2 branches that are going to start at poles and end up at zeros because we have 2 zeros. But now we have 3 poles that we do not know where they're going to end up at. And these 3 poles are going to end up at infinity through an asymptote. Does that make sense? So remember also, we mentioned that if we take any system, the number of poles and number of zeros that the system will have is always equal if we consider s when s goes to infinity. So if I look at a system like this, how many poles this system has? 3 poles. How many zeros it has? Very smart. This does not look, it has any zeros, does it? But we said if I were to take the case when s goes to infinity, then this has 3 zeros. Does that make sense? This has 3 zeros that are at infinity. Together? When s is infinity, I can ignore the 1 here. I can ignore the 1 here. This is almost equal to k over sc cubed. When s is infinity, what is this value equal to? 0. Isn't it? So it is a 0, but this 0 is at infinity. Now this is something new we're not used to. We're usually used to a finite number of poles and zeros. But here we have an infinite 0. Make sense? So this is the new thing that we're going to be using, which is we're always giving any system there is equal number of poles and zeros if we consider the infinite zeros. Make sense? Okay. So we said, so continuing to our lecture here. So continuing with the rules. Now is the rule on the real axis more clear? Why we said the real axis, let me actually go back also to lecture 15 and go over the rules. Is the rule clear that on the real axis, the part of the real axis that belongs to the root locus is to the left of an odd number of poles and zeros? Clear? Based on the angle criteria?
I remember it, but I don't remember why.
Oh, yeah, we did not make you why, but that's why we did what we've done before this, which is the angle criteria.
It's on the axis, so it's always going to be 180.
After the first one to the left, they stop.
Because of this. Because we're going to do the angle criteria. If S1 is on the real axis, all the poles that are off the axis, their contribution is going to cancel out. A pole on the right is going to contribute 180. A pole on the left contribute 0. Make sense? A 0 on the left is going to contribute 0. On the right, 180. Together? So the only way I'm going to have 180 if I have on the right an odd number of poles and zeros. Make sense? an odd number of poles and zeros. Why is it an odd number and not an even number?
Even number would be 360.
It will be 360. An odd number, I could have two poles, 1 0, 360, 180, it's 180. Does that make sense? I could have two zeros, one pole, 180, 180, and minus 180, it's 180. Is that clear? So therefore, on the real axis, S1, the part of the real axis that's on the root locus, to the left of an odd number of poles and zeros. I plot the poles and zeros, and then I'm going to mark to the left of an odd number of poles and zeros, and I know that is going to be part of the root locus. Together? Everybody? Okay. So that was a rule. And the second rule, we say, or another rule, we say we're going to have a number of asymptotes that is equal the number of poles minus the number of zeros. What does that mean?
How many infinite?
Excellent. That is how many infinite zeros we're going to have that our root locus is going to end at is going to equal to the difference between them. Remember, we said every pole is going to end at a 0. So if I have 5 and 1 0, I have one of the poles that's going to end at that 0, and I still have 4 that's going to end up as asymptotes. Make sense? So alpha equal number of poles minus number of zeros, meaning number of finite poles minus number of finite zeros. Make sense, everybody? Okay, we'll do an example. Later. We're going to do examples to illustrate these. So again, the root locus is going to start at finite poles and end at finite and infinite zeros. These infinite zeros are going to be the asymptotes. Together? Okay. And finally, we also say when we plot the root locus always starts at a pole and always ends at a 0. When we increase k, the root locus is going to go from the pole all the way to the 0. So when k is small, I'm going to be operating here. When k is large, I'm operating here. As k increases, my roots are going to be moving all the way to the 0. When k is infinity, I'm going to be at this point. And we illustrated it with this example here. So everybody should be convinced. It's slightly confusing, but hopefully with the example it should be straightforward. Sounds good? Okay. So from the previous rule, we said we're going to have asymptotes that are going to equal to n minus m. Now, there is also another rule that will help me know what angles these asymptotes make and where they meet. So we call that the intercept, which is going to equal to, given by the summation of finite poles minus summation of finite zeros over the number of finite poles minus number of finite zeros. And we have the angles that these asymptotes are going to make, which is equal to this formula here. Good? So let's see what all this means. Again, I know it's overwhelming, so if you feel overwhelmed, calm down. Again, we're going to explain each rule. I'm going to convince you the rule makes sense. Then we're going to go to the next rule, and you're going to be confused. Oh, but the first rule, you said it starts at, how do I put these together? But at the very end, hopefully, when they all come together, you feel like, oh, this is straightforward. And on the day of the exam, you forget all the rules. Okay, so let's do an example. Go ahead.
So last lecture, when you first used MATLAB, it seemed like you had like 7 lines of code. I guess use on Alice, is this supposed to be easier, or is it just proving? What's the benefit of doing it by hand versus using MATLAB, if there is one?
Very good question. And since we are recording, I have to be very, watch what I say.
Okay.
You can do this in MATLAB with one line, not with 7 lines. One line. Together? You can do it with one line. But what happens if you are in the middle of the desert and you don't have access to MATLAB?
Then I'm worried about finding water.
Okay, let me qualify my question. If you are in an oasis,
Then I'm worried about finding rum.
no, a good question. We can use MATLAB to plot it, isn't it? Then why are we doing all this work? You see? So we can understand what MATLAB is doing. Because you can do a type. Sorry? Go ahead.
I just wanted to make sure that that was the answer and not, I wasn't missing some piece to this then.
No, that's the answer. I mean, this existed before MATLAB existed. You see what I'm saying? They're plotting the root locus. MATLAB came and said, oh, you guys doing root locus? Oh, let me make it easier for you. Here, you just do root locus. We said, okay, great, we'll use your root locus. But I have to know what the root locus is in order to use it. Does that make sense? Just like a calculator. If you multiply 5 times 3, what do you expect to get? A 15. If you get, negative 15, you can say, I must have done something wrong. But you cannot say, then why are we learning the multiplication? I can just use a calculator. Make sense? Now that is one thing, which is understanding the logic behind the root locus. And also, doing the root locus will help us better understand the system. Make sense? Like how the system, what is the impact of the gain on the system? Answer your question?
Yeah, that answered it. Thank you.
You're welcome. Okay. Okay, so let's do an example on the calculation of the asymptotes. Okay, so we have this system. And I want to see how the asymptotes of this system look like. And we'll explain what the asymptote means. Anyway, we do not even know what asymptotes. Anybody knows what asymptotes mean? So some of you might not even know what we mean by asymptotes. We'll clarify it. So looking at this system, if I look at g of s multiplied by h of s, how many poles do I have? 4. You see it, everybody? What are the poles that I have? A pole at 0, -1, -2, -4. How many finite poles I have of the system? 4. How many zeros do I have on the system? Now I have to be careful. I'm going to say how many finite zeros I have on the system. 1 at -3. How many infinite how many infinite zeros do I have? 3. Which means when s goes to infinity, when s is very, very, very large, it's going to give me 3 zeros. Together? Okay. So what I want to calculate, I want to plot the asymptotes. So I'm going to go to the formula that we just listed. We did not explain where it's coming from, isn't it? So we're going to calculate the intercept, and we'll see what this means. But the formula says your intercept is equal to the summation of the finite poles minus the summation of the finite zeros divided by the number of finite poles minus the number of finite zeros. So this is going to equal to 0, minus 1, minus 2, minus 4, minus the zeros divided by the number of finite poles minus the number of finite zeros. Together? So here we have 4 poles, we have 1 zeros. So this is the 4, this is the 1, and then we have these, the actual poles, and the actual zeros. Is that clear? Go ahead.
Did you say the bottom was the number of poles, finite poles?
Yeah, the number of poles minus the number of zeros. Number of finite poles minus number of finite zeros. So this 1 is here. Make sense? So this 4 is here. This 1 is here. And these are the actual zeros and the actual poles. Make sense? Okay, if we calculate this, this is going to equal to negative 4 over 3. Then we're going to calculate the angles. And theta A is equal to 2k plus 1 multiplied by 180 degrees divided by the number of finite poles minus the number of finite zeros, which is 4 minus 1. And we're going to calculate it for k equals 0, 1, and 2, since we're going to have 3 asymptotes. Together? How do I know I have 3 asymptotes?
4 minus 1.
What is it?
The 4 minus 1.
4 minus 1, yes. Number of finite. So here we have 3 asymptotes, which is the 4 minus 1, which is equal to a 3. And therefore, I'm going to take theta A for k equals 0, 1, 2, all the way to 3 minus 1. Make sense? Alpha equals 3 asymptotes. Therefore, alpha, which is the number of asymptotes, is equal to 3. We're going to take from k equals 0, 1, all the way to alpha minus 1. So therefore 0, 1, and 2. Now if you take any larger values, you're going to be getting the same answer, the same angles. Does that make sense? So I could have taken 0, I could have taken 0, plus minus 1, plus minus 2, plus minus 3, but I'm going to end up going back, generating just 3 angles that are unique. Okay. So when k is 0, I'm going to get 2 times 0 plus 1 times 180 divided by 3, which is going to equal to 60 degrees. When k is, this is when k is equal to 0. When k is equal to a 1, I'm going to get 2 times 1 plus 1 minus multiplied by 180 over 3, which is going to equal to 180 degrees. When k is equal to 2, is going to equal 2 times 2 plus 1 times 180 divided by 3, which is going to equal to 300 degrees. Now on the side here, I'm just going to write it if you're ever confused So you can go to MATLAB and just type this. If I were to take k from -10 to a 10 and calculate wrap to 180 of 2k plus 1 multiplied by 180 over 3, I'm just going to get 60, 180, and -60. And I could have done it to any angle, doesn't matter, even minus 1,000 to 1,000. I'm going to only get these three unique angles. Oh, -60, which is the same as 300. Together?
Do you have to do 2 star K or just 2K?
No, it's the formula. 2k plus 1.
I'm talking about
Multi-
MATLAB.
Which one?
In MATLAB, do you have to write 2 star K? Like 2
Yeah,
times
yeah,
K?
just start. To star k plus 1. Okay. So what does all this mean? Let's see. So I'm going to come here, and now I'm going to plot my root locus based on what we learned so far. What is the first step when we plot the root locus? The first step is we're going to mark all the open loop poles and zeros. So if I come here, I have a pole at 0. I have a pole at -1. I have a pole at -2. I have a pole at -4. So -1, -2, -4. And I have a 0 that is at -3. So this is my 0. Together? Now, which part of the real axis is on the root locus? 3 to 4. Is that it? 3 to 4. To the left of an odd number. That seems an odd number. Okay. So let's start from the rightmost. Is this part of the root locus?
Yes.
Yes. Is this part the next one? No. Is this part of the root locus? Yes. Is this part of the root locus? No. Is this part of the root locus? All the way to infinity. So these parts are of the root locus. Okay, since we are at this, so when k is very, very, very small, when k very small, where am I going to be operating? At these poles, isn't it? As I increase k, I'm going to move away from this pole. 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 Agree? Okay. Now this pole, when I keep increasing k, where am I going to go? To infinity. Perfect. Solved. When I increase k, where am I going to end up here? What is it?
-3.
At the 0. Yes, at -3. Perfect. When I increase k here, notice when I increase k, I'm going to be moving away from this pole and away from this pole. I have two. So I'm going to be moving away from them. What do you think is going to happen?
-0.5.
Eventually, I have to leave these to go to the 0 that is at infinity.
So like that.
We'll plot it, yes.
Okay.
So
Whatever this is.
I know that I have three asymptotes, and these asymptotes are going to meet at -4/3, which is what we calculated, which is -1 1/3. So -1 1/3 is this point here. that you cannot see. Can you see it? Negative 1/3, 1 and 1/3. So what my calculation said is that if you come here and plot a line that makes an angle, what is this angle? 60 degrees. Plot another line that makes an angle. What is this angle? Negative 60 degrees, which is also equal to 300 degrees. And then plot a line that is equal to what? 180 degrees from this. Then these are the lines for asymptotes. Together? Now, how does the root locus look like? We do not know, but I'm going to tell you the root locus looks something like this. Together? And this is what these asymptotes mean. This is an asymptote, this is an asymptote, and this is an asymptote. And these are the angles they make, 60, 180, and negative 60. Any questions? Questions?
I don't know if I see how 180 is an asymptote.
This one? I mean, if I come here, I do a 60 degrees, I keep increasing it, it's 180 degrees. Why? What's your objection to the 180?
Does it really have an effect?
I guess I'm trying to picture like the little X's from MATLAB, and I can see the two branches like that.
MATLAB did not tell me how these are going to leave, isn't it? Sorry, not MATLAB. The asymptotes, the formula, did not tell me what happens here. But the asymptotes told me when S is very, very large, it's going to be adjacent to this line here. When S is very, very large, it's going to be adjacent here. When S is very large, it's going to be adjacent to here.
Okay.
Does that make sense?
Yeah.
I used other knowledge to do this, and to do this. With me?
Mm-hmm.
This, we do not know. Like somebody might ask you, look, why did you decide to leave like this? Somebody might. Anybody? Nobody? Okay. So this we did not cover yet, but we'll cover it. This was clear because we already have a rule that says I have to be to the left of an odd number. It just so happened, yes, I'm doing the odd number. The two things work together. Does that make sense? This was straightforward to figure out because it happens to be to the left of an odd number of poles and zeros. This one, this is what the asymptotes, this part is what the formula for the asymptotes told me. This part, and the fact that if I were to stretch these lines, extend them, I'm going to be meeting at this point here, which is negative 4/3. Make sense?
So you could have a point S anywhere on those orange lines, and it would be part of the root locus?
Yes, this is the root locus. Yeah, I could have, for a certain value of k, I could be operating here, I could be operating here, and there's one here, there's one here. I could be operating here, here, anywhere. This orange, the orange plot that I have is what the root locus. This is the only place this system is going to have poles.
So in between those,
I have a question.
Go ahead.
So I understand the asymptotes and how they affect the angle. Can you draw another plot past the -4? I'm having a tough time grasping how the 180 degrees affects it.
It's just basically, it's a line along the negative axis. What I'm not, did I, go ahead, explain what is the...
So like the slope of your orange line you draw there, I understand how the asymptotes affect that,
Yes.
because they, as it goes on to infinity, they approach but don't ever touch that. But I guess the 180 degree part,
So this is what the asymptote, what the formula told me about the asymptotes. I have one that is at 60 degrees, one that is at 180 degrees, and one that is at negative 60 degrees. And they all meet at this point here. They meet. The asymptotes, which means the line parallel to the root locus, are going to meet at negative 4/3.
Okay.
Make sense? So I can take this template that I just plotted, put it on top, and say, okay, this is my guidelines for where the root locus is going to be. It's not the root locus. You see here, if I look here, the root locus did not start from this point. Does that make sense? So this is just a guide of where this branch is going to go. There is a branch that is, when s goes to negative infinity, is going to be on the root locus. With me?
Yes.
When s is very large, it's going to be going at 60 degrees. So it told me about how it behaves here, how it behaves here, how it behaves here. But the rest of the details, I have to figure it out. It told me this. But since I know it's going to be like this, I had prior knowledge that also it has to start here. It makes sense. This is going to be one line. There's nothing that's going to make it not continue all the way to infinity, negative infinity. Answer your question?
Yes, it did. Thank you.
You're welcome.
So in between pole 1 and 2, is there like a vertical asymptote, and that's why?
No, there is between 1 and 2, negative 1 and negative 2.
No. Pole 1 and pole 2.
Pole 1 and pole 2.
Pole 0
0.
and pole 1.
Pole 1.
Yeah. Is there a vertical asymptote between those two, and that's why the thing?
No,
goes in the middle?
yeah. These are going to go vertically, but this is not called asymptote. Asymptote is only when s goes to infinity.
Right.
Does that make sense?
Okay.
So this is the S space. When the space we're looking at is our S space. Good? This is the S space. If I am at this point, I am at negative 1 plus J1. If I'm at this point, negative 1,000 and J 1,000. If I keep going farther and farther and farther, what is this going to go to? Infinity. In this case, it's going to go to an infinity with angle that is 135. Make sense? So very far away, it tells me what happens when we are very far away, when s goes to infinity. It does not tell me anything about when s is very small.
Okay. I
Make
didn't
sense?
know if maybe that's why it went in between those two poles.
No, it did not.
Okay.
How this behaved here, I'll take it off. You know what? Here. Oops.
Uh-oh.
Only if I could delete it, I would have deleted it. We do not know why it went like this.
Okay.
The only thing this formula told me is this, meaning like up to my hand, and this.
Okay.
This, we're going to figure out in another rule, why it broke like this. However, what we should already know is that what we said, which is the root locus starts at the pole, ends at the 0. So when I look here, and I have a pole and a pole, it's going to bother me, isn't it? Because we said it's going to start at the pole, it's going to end at the 0. I mean, if I were to look, it looks like, oh, I'm going to start here and here. No, I'm not going to start here and here. One is starting here, one is starting here, and as k increases, we're moving away from the pole. So the only way, when k keep increasing, the only way I'm going to be able to continue is if I leave this axis and go somewhere else. Make sense? Okay. Any other questions? Honestly, like it's probably one of the most fun things to do is to plot the root locus. I mean, once you... I'm not using MATLAB. Okay. And after we finish all the rules, you can, like, if you're ever bored, you can challenge MATLAB. Try to plot the root locus and try to do it faster than MATLAB. Okay, so we are given this system Okay, so if you look at this system, how many finite zeros and poles? We don't have any finite zeros. We have infinite poles at two, that are 2, and we have poles finite that are 2. So therefore, I'm going to go to my asymptotes formula and calculate the intercept. It's going to equal to -1 minus 3 minus the location of the zeros, which is 0 because I don't have any zeros, divided by the number of finite poles minus the number of finite zeros, which is going to equal to -2. I'm going to calculate theta of the asymptotes is going to equal 2k plus 1 multiplied by 180 divided by number of finite poles minus number of finite zeros, which is going to equal to a 2. And when k is equal to 0 and a 1, it's going to give me theta A equal to 90 degrees, and it's going to give me 270 degrees, which is the same as -90 degrees. Together? Let me try to zoom this so we can fit it on one page. Okay, so we're going to plot the root locus for this. What is the first thing we're going to do? We're going to plot the axis. The rules keep changing. Okay, after we plot the axis, we're going to mark the poles and zeros. So in this case, we have a pole at -1, and we have a pole that is at -3. Which part are we on the real axis that is part of the root locus? Between -1 and -3. Very good. So we know from previous rules this is part of the root locus. Now the asymptotes that we calculated told me this. It told me that you're going to have two asymptotes that are at angle 90 and -90. And these asymptotes, if you were to stretch them, they're going to meet at -2. So what the asymptotes calculation told me, at -2, you're going to have an asymptotes, and you're going to have an asymptotes, this at angle that is 90 degrees, this is at angle that is -90 degrees. Make sense? This is what the asymptotes calculation told me. I have a 90 degrees. If I were to stretch it, it's going to meet at -2. Stretch it, meet at -2. Now I'm going to take that knowledge and say, okay, can I now plot the root locus? What do you think the root locus is going to look like? A vertical line, yes. Can you have it any other way?
Maybe.
This will not go to the center. So now I'm going to do? I'm going to accommodate it. Any objection? Anybody? Objection? No?
I did have a question.
Mhm.
So if it's inside the yellow, like, if it's inside the poles, -1 and -3, we don't draw, like, the blue line, and we just draw out the yellow line?
Meaning the blue line and yellow line?
Yeah,
This one?
yeah.
No, I did this intentionally. I would have put it here, but I want people to understand this is like a guidance of how the plot is going to look like. You know what I'm saying? Like, if I were to, because somebody, or I felt like somebody might have got confused with that thing, I put it on the side. Otherwise, I would not have plotted this. I would just have come directly here and said, okay, this is asymptote, this is asymptote. They're meeting at this point, and I would have connected it. Make sense? And again, you won't have to do this like when you're plotting the root locus. But visually, in the back of your mind, this is how it looks like, so you apply it here. Go ahead.
So for the root locus, it's defined by the asymptote. Do we care about which side of the asymptote it's technically on?
Meaning?
For asymptotes, you don't ever actually touch them, right?
At infinity, you're almost on top of them. Yes.
Okay. So it doesn't really matter.
So it gave me the guide there. It gave me the guide here. It told me it's going to meet here. I know this is going to break. I can calculate the point they're going to break at. And then add them all together. This makes sense. Makes sense? Like somebody could have objected. Somebody could have objected and said, oh, why did you plot it like this? Why did you not plot it like this? What do you want? Why did I not plot it like this? I mean, this will be valid according to my asymptotes rule. Make sense? This is a valid graph. Asymptotes at 90, asymptote at negative 90. They meet at negative 2. Why did I not do it like this? Nobody objected, so we have to do this. I mean, it made sense to me that it will be like this. Makes sense? I could have calculated, later on, we'll calculate this point that tells me it's going to break at this point. So if I calculate this point, then apparently this is not valid. Makes sense? And therefore, again, later on, we'll see why it is not like this. But also, I'm expecting some symmetry of how this is going to behave when I increase k. It makes sense to break at one point. I mean, how does the root locus as I vary k look like? When k is very, very small, I'm here. I increase k, I'm moving away, increase k, moving away, increase k. Eventually, I am at this point here. I increase k, I'm now at this point here, and at this point here, and so on.
Immediately becomes imaginary with no real part.
No, there is a point here where they're going to be on top of each other. Make sense? And at this point here, what is the response of the system going to be? Critically damped. So there is, if I look at this system, it's second order. When I'm here, I'm over damped. I keep increasing k, I'm going to become critically damped. I keep increasing k, I'm going to become under damped. Together? And it is a second order, so it's easy to plot the characteristic equation, see how k is affecting it. Any questions? Okay. Let's wish you all a great break. Don't forget to study in the break.